As you've seen, a logarithm has a particular number called the base. And the base can be any positive number you want it to be, as long as it's not base 1. And that goes along with our simple exponential function that we introduced in the last section. Where the base had to be a positive number of an exponential function, could not be equal to 1. The same goes with the bases of logarithms because they are linked together. And but there are two special kinds of logarithms for which you have calculator buttons. We all do on scientific calculators, and that's the common log and the natural log. And so if you see log of something, x or some number, without a base written, if there's no base written, that's known as a common log. It's the base 10 log. So the common log is understood to be base 10. And base 10 is, very convenient, of course, because we live in the base 10 world. And so 10 is the most, natural number we have in some sense for this purpose. So if that's blank, it's base 10. And you'll see an log key on your calculator. It'll just say log, log. That's the common log, base 10 log. So you might try, for example, punch in the log of 2, and I think you'll get 0.30102999. I want to check myself. Now, the log of 2 and I go back a long way, so I tend to remember it pretty well. Yep, 0.30102999. Actually, there's more 9s after that, so it's... Anyway, it's approximately that. That's the base 10 logarithm. The other special logarithm that for which you have a key is the natural logarithm. And it's written as ln x, or ln of a number. And it's literally the log base e of a number. We call it natural log. So, but normally we write ln x. We don't write this. But the base is e. E our special number, 2.718. Ln log actually is much more useful these days. You see, logarithms up until the early 1970s, logarithms were used to compute things, to do fast multiplications and divisions and square roots and cube roots and things like that. Logarithms were very valuable to paper and pencil calculations. Once that these started coming on the market around the early to mid 1970s, then we no longer had a need to use logarithms for computational purposes. I've had one instance in the past 20-some years where the only way I could calculate something was to use logarithms, where I had to use logarithms for computational purposes. That's because the problem was actually larger than a calculator or a computer could have stored. The numbers were so big. So it's almost never used anymore for that purpose. But logarithms are very important in mathematics, and so they show up in a lot of places, particularly when we're trying to solve problems involving exponential functions, and there's many other uses out there in the real world. You just, again, this course you just get a very small glimpse of logarithms. So they're still very important. But I would say nowadays the natural log is far more important than the common log because we don't really use this much anymore for computation. But I'll show you where this comes up. The common log is associated with some scientific scales. For example, the Richter scale, measuring earthquakes, is a logarithmic scale. And so, for example, if you went through an earthquake that was 4.6 on the Richter scale, and I've been through an earthquake like that out in California. I experienced one of those, and it gave quite a shake. It didn't cause much damage, but you definitely felt it. If you compared an earthquake of 4.6 on the Richter scale to one that's 6.6, if you're familiar with the Richter scale, you know this is a very serious, deadly earthquake. These are big ones. 6.6 is 2 larger than 4.6. That means it's power, its energy, is 100 times as much. And so these numbers, Richter numbers, are associated with powers of 10, and in a sense these are logarithms. And so by comparing, if this number is 2 more than that, that means it's 10 squared 100 times as powerful. If you try to imagine then, what would the largest earthquake ever recorded that we think was around 9.0 on the Richter scale. There's been 2 or 3 of those in recorded history that we think were around 9.0 on the Richter scale. One was the New Madrid earthquake in New Madrid, Missouri, which is sort of near Memphis, Tennessee. Around 1811, 1812, I forgot when. It actually was so powerful, it rang church bells in Boston, and it made the Mississippi River flow backwards for 3 days. And it actually rerouted this Mississippi River. It was enormous. Fortunately, hardly anybody was living out there in 1811. But there was, I think, possibly the one in Alaska in 1964 on Easter morning. I remember that one. Believe it or not, I'm old enough to remember that Alaskan earthquake. I think it was very close to 9.0. There may have been one in Mexico like that too. Anyway, I went through a 4.6 Richter scale earthquake, which really shook the house. I mean, the bed, it was in the middle of the night, I woke up, and I was sitting on the bed, and the bed was going like this. It was just swaying back and forth. And that was just a little earthquake. Okay. How much more powerful is one of these? And so 9 minus 4.6 is 4.4. 10 to the 4.4 power is very large. That's around 25,000, we'll say. Roughly 25,000 times as powerful. I can't begin to imagine what that kind of earthquake would be like. It would be very, very deadly. So, fortunately, they're extremely, extremely unusual. But anyway, to give you an idea, the Richter scale is a logarithmic scale. The decibel scale for hearing, for sound, loudness of sounds, is a logarithmic type of scale. And a decibel is 1/10 of a bell. A bell is a power of 10 in energy. Anyway, we measure the loudness of things on a scale that is sort of logarithmic. Let me see, another one is the pH scale, measuring acidity or alkalinity in chemistry. And there's a few others that I can't think of off the top of my head, but there are some scientific scales that are based upon logarithms. So even the frets on a guitar, if you own a guitar, if you look at the frets, how they're unevenly spaced. Near the top of the neck, the frets are spaced out farther than when you get toward the middle of the instrument, toward where you're strumming the guitar. And so those spacings are based upon logarithms. So anyway, there's some applications of logarithms, but base 10 logarithms are still used somewhat in some places in science. Mostly, however, we worry about natural logarithms anymore. So anyway, let's try a calculation on your calculator. Can you calculate the natural log of 13? Okay. So find the LN button on your calculator, and it is probably right above the e to the x button. Or I might have that backwards. Maybe you have ln and then e to the x is above it. But they're always together. Like on my calculator, I've got ln is the button, and above it in fine print is the e to the x. So I'm going to hit ln 13. And I get approximately 2.565. And so you should get that. It's possible you have to hit 13 and then the natural log. On my calculator, you hit natural log and then 13. So anyway, there's those two logarithms. You should be some familiarity with natural logs and common logs.